Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about trigonometric functions. Only thing we need to review before we get into it is reference angles. Now, I've talked about reference angles a little bit in past videos, but not to the extent that we're about to go through. Okay, starting with kind of the main stipulated definition here, which says that for any angle theta, the reference angle theta sub r is the positive acute angle made by the terminal side of theta and the x-axis. If you have an angle here, this is a quadrant 2 angle, maybe it's like pi over 3 or something like that. If you think about the angle that's made by the terminal side of theta and the x-axis, what we're talking about is this angle right here. Okay, that's the reference angle. In quadrant 3, the reference angle is here, and in quadrant 4, the reference angle is here. In quadrant 1, the reference angle is basically itself, right? Because it's the terminal side of the angle and the side and the x-axis that construct the angle measurement. Well, in this case, both the original angle and the reference angle are the same one, okay? Now, the reason I called it a quadrant 1 angle is because all of these reference angles are congruent to a quadrant 1 angle with that exact same measurement. Based on the way that the reference angle is defined, it's never going to exceed pi over 2. So we can always redraw it in quadrant 1, and so that's the way that I think about it. I think about it as the quadrant 1 angle that's going to give you similar input and output values for all of your trig functions, right? For sine, it's the y-coordinate. For cosine, it's the x-coordinate. The one thing that we don't know for sure is the actual sign, S-I-G-N, right? The plus or minusness of the value itself. But this is why I refer to it as a quadrant 1 angle, is because all reference angles are between 0 and pi over 2. And so you can just redraw some congruent angle in quadrant 1. And this is what I was talking about. You're always going to get the same kind of output for all of your trig functions when you plug in a reference angle. The only exception, right, the only kind of main differentiating factor between using a reference angle and using the original angle is the sine value of that particular angle measurement, right? So if you're plugging in something in the third quadrant, it's a theta measurement in the third quadrant, sine is supposed to be negative there. But if you take the sine of the reference angle, you're going to get a positive value no matter what. And that's actually true for all of your trig functions. All the trig functions are positive in quadrant 1. So that's why when you're using a reference angle, you're getting the same value, but its sign is different, right? So you could be potentially getting the opposite of the value that you want. So for example, if you plug in like 7 pi over 6, right, whose reference angle, by the way, is pi over 6, you can draw the corresponding quadrant 1 angle and just notice that it's the same value. Its sign is the only thing that's different, right? In quadrant 3, both the x and y coordinate, cosine and sine respectively, are negative. But if you're plugging in the reference angle, right, theta sub r, you're going to get only positive values. So that is something to keep in mind, but it's actually really easy to use and super useful. And speaking of usefulness, this is used for evaluating trig functions, which I'm going to show you a very brief example of here in a second, and also kind of stuff we've already been doing. But then we're going to extend the idea to solving trigonometric equations in general. Let's say you want to solve, or you want to evaluate, for example, the cosine of negative 11 pi over 3. Well, instead, I'm just going to evaluate the reference angle pi over 3. Right? And actually, finding reference angles is really nice when you're working in radians, because it's just the pi over whatever the denominator is, right? The reference angle for 112, pi over something, 4. Now that simplifies. 112 over 4. I don't know, 113 pi over 4. The reference angle is pi over 4, right? Negative 2,331 pi over 3. I don't know if that simplifies. Let's pretend that it does not. The reference angle is just pi over 3, right? So that's the really easy and nice thing about reference angles in terms of radians. So in this case, you've got your original angle of negative 11 pi over 3. The reference angle then is pi over 3. And because, hopefully, at this point, we're all, on point with knowing the quadrant 1 outputs for sine and cosine, we should know automatically that the cosine of pi over 3 is a half. So by the way, we know that cosine of negative 11 pi over 3 is also going to be 1/2. What we don't know is its plus or minus value. Is it positive or is it negative? Well, you could, there's multiple ways to figure out what quadrant that specific angle is in. You can count them out. Keep in mind in this case, though, you're counting clockwise because it's a negative angle instead of counterclockwise. I look at this and I say to myself, look, this is only pi over 3 more than negative 12 pi over 3. So it's almost negative 4 pi, but it's not quite negative 4 pi, right? It's pi over 3 more than 4 pi. So then I just go pi over 3 more than 0, and that lands you in quadrant 1. So it's positive 1/2. So that's a reference angle. You can use that for reference. Let's do some examples. All right, so for example 1, let's say we want to solve 2 sine squared t minus 5 sine t plus 2 is equal to 0. You want to get sine t by itself before you inevitably take the sine inverse, take the arc sine of both sides to figure out what t is supposed to be. So I would think about this as a quadratic expression, but instead of sine t, you've just got like an x or something like that. 2x squared minus 5x plus 2 does factor. It's 2x minus 1, 2x minus 2, so you break this thing up using the zero factor property or the zero product property or however you know it. That's the approach that we're going to take here. 2 sine squared minus 5 sine t plus 2 is equal to 0 does factor. It factors into 2 sine t minus 1 times the sine of t minus 2. You can use the zero product property to set each of these things equal to 0, but notice that the one on the right does not have any solutions. The sine of t does this maneuver, and y is equal to 2 is up here. So they never intersect, so this thing's got no solutions. Okay, well that's nice actually. Let's just focus then on 2 sine t minus 1, right, is equal to 0. So first you'll add 1 and divide by 2 to get the sine of t is equal to 1/2, at which point now we're going to take the arc sine of both sides. Oh, by the way, and so here's where reference angle stuff comes into play. If this were negative, I would really be focusing on a reference angle. This one's already positive, so some might argue, Mark, what's the point of using a reference angle here? I think it's still useful, and I'll show you why here in just a few minutes. But this is a step that I always take, so I really should have a kind of a step before this that says the sine of t is equal to 1/2. I would like to consider the reference angle, which automatically turns whatever this thing is into a positive, right? That's one of the properties of reference angle stuff, now that we're just considering a quadrant 1 angle. But this one was already positive, so there was really nothing to change. I just added the reference subscript to the angle t. Taking the sine inverse, taking the arc sine of both sides, is going to yield that the reference angle is pi over 6. And at this point, this is where I'd like to stress, this is why I'm using a reference angle. If you just said t is equal to pi over 6, we're not done with this problem. There's still quite a bit to unpack here. Pi over 6 is a solution. Typically, trigonometric solutions actually have multiple solutions. A lot of times, they have infinitely many solutions because of the fact that trigonometric functions cycle, right? They're periodic functions. They always repeat themselves over and over and over again. So pi over 6 is surely a solution, but then anything coterminal with pi over 6 is also going to be a solution. And in fact, there might be other angle measurements that also give you 1/2. Right, that also make this thing 0, right, when you plug them into t. And so that's why I really like to use this. Look, what we just found is the reference angle. Now we need to unpack what kind of solutions are there? How many solutions are there? If you look back at the problem, there's something that's missing right here, right? Something should be right here that tells us what it is that we're solving for. Something like this, right? Maybe it's you've got, you're solving this thing, but where t is on the interval 0 to pi over 2. If t is on the interval 0 to pi over 2, then okay, we're done, right? T is equal to pi over 6. That's the only solution that's going to be in quadrant 1. Pi over 6 is the only angle in quadrant 1 that, satisfies the equation. So we're done here, right? But what if it said 0 to 2 pi, right? Now, there's more than one solution, right? You can certainly have pi over 6. That's a solution to this thing. But there's also another angle that produces a 1/2 y coordinate on the unit circle, and that's in quadrant 2, and it's 5 pi over 6. Okay, so now we've got two solutions. By looking at a little bit of an expanded interval here, now we've got two different solutions. What if we were going negative 2 pi to 0? Well, then this isn't a solution at all, right? Pi over 6 is not in the interval negative 2 pi to 0. So now we got to think about what are the negative angles inside of the interval negative 2 pi to 0 that give us 1/2, right, for sine. Right, and so this is, again, I'm kind of stressing, why am I using a reference angle and not just saying, well, that's just t in this case. T is pi over 6. And again, it's because it really depends on this, right? This is just a reference point. It's a point of reference for us to determine what the solutions are. If our interval is negative 2 pi to 0, I'm going to use pi over 6 as a reference angle, right? And I'm going to find the negative coterminal angles for negative or for pi over 6 and for 5 pi over 6, right? Because the reference angle is here. So if I take away or if I add the reference angle to negative 2 pi, I'm going to get negative 11 pi over 6. If I take negative pi and I subtract away negative pi over 6, that's going to give me negative 7 pi over 6, right? So those are the two solutions then in this particular case. So again, it really depends on what goes here. And you'll notice that in the original problem, there is nothing. Nothing's listed there. So then we can really think about the interval that we're solving this on as all real numbers, negative infinity to positive infinity. T is inside of that interval, which is anything. So that means that pi over 6 is one of the solutions, but anything that's coterminal with pi over 6 is also going to be a solution. So we got pi over 6, 13 pi over 6, 25 pi over 6, 37 pi over 6, right, so on and so forth. And that's not even counting the negative angles that are coterminal with pi over 6, like negative 11 pi over 6, negative 23 pi over 6, right, so on and so forth. That same thing happens for 5 pi over 6. 5 pi over 6 also satisfies the original equation, but anything that's coterminal with 5 pi over 6 then would also count as a solution to this thing. And one of the things that I want you guys to notice when you're looking at this is that as you increase, as you look at all these solutions, to get from one to the next one, you're adding 2 pi because they're all coterminal with each other. So these are all the coterminal angles with pi over 6. Same thing happens with the 5 pi over 6 stuff. You're just adding, it's anything coterminal. So if you just add 2 pi to the previous value, in that second pattern, you're always going to come up with another solution to this equation. So rest assured, you don't have to write this every single time when you're solving on an interval that's not given, which is to say you're solving on the interval of all real numbers. Instead, you can quantify this by doing something like this. Here I said t is equal to pi over 6 plus 2 pi times n, where n is an integer. Right? This is the symbol for the integer number system. Integers are all whole numbers that are positive or negative, and including 0. And so this is what I call the generating set for the first solutions of t here. And you could plug in whatever you want for n, that's another solution. You could plug in 0 for n, and then that would just be t's pi over 6 is a solution. You could plug in, negative 1 for this thing. So then you'd be subtracting 2 pi from pi over 6. Well, that's negative 11 pi over 6. Right, you could add 3 times 2 pi. So n could be 3, then you'd have 6 pi that you're adding to this thing. I believe that is going to be 37 pi, right, over 6. Right, so that's it. You're coming up with what I call generating sets for the solutions of t. And then you're going to do the same thing for 5 pi over 6. Anything that's coterminal with 5 pi over 6, so that we're adding on this plus 2 pi n thing where n's an integer, and this tells you, look, plug in anything you want for n, and what you get when you add that to 5 pi over 6, that's going to get you, that is also a solution, right, for this thing. So these are really not, maybe saying that t is equal to these things could be a little bit misleading. This is how we would generate solutions for this thing, right, is with pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n. Now, I know that's a lot of information right up front in the first example, but let's do another one, and we'll kind of, hopefully this starts to get solidified a little bit. So the moral of the story here, though, is always check what your interval is. If nothing's given, right, don't just assume you're finding one solution. In fact, if nothing's given, I would assume you're finding all of them, which in trigonometric terms is actually usually an infinite amount of stuff, since, again, trig functions are periodic. They repeat themselves. Okay, example 2. Solve 2 tangent of theta is equal to secant squared theta. Now, 2 things. 1, notice no intervals given. Okay, so we're going to need to do some plus pi n stuff. And then also, something to keep in mind is typically when I'm solving trig functions, and this is kind of an additional level of complexity from the last example, try to write your equation in terms of only one trig function so that you can do something like factoring. In this case, we've got 2 different trig functions, and automatically that's like, well, that's going to be hard to solve if we don't replace one of them with a similar trig function. So we have identities, right, that we can use to rewrite this thing, and that's the first thing that I would do here. So again, no intervals given. We're working on all real numbers here. So first thing I'm going to do is I'm going to turn secant squared theta into 1 plus tangent squared theta. And we can do that because of a Pythagorean identity. So 2 tangent of theta is equal to 1 plus tangent squared theta. Cool. Now I'm going to treat it like a quadratic. I'm going to get everything on one side, reorder some stuff, and then I'm going to think about this as x squared minus 2x plus 1, which is actually pretty easy to factor, right? It's just x minus 1 and x minus 1. So this thing factors in the tangent theta minus 1 times tangent theta minus 1, or maybe more simplistically, tangent theta minus 1 quantity squared. And to solve that, I'm going to square root both sides, which typically gives you plus or minus stuff, but since 0 is on the left-hand side, plus or minus 0 is the same thing. So we have 0 is equal to tangent theta minus 1, or tangent theta is equal to 1, at which point I'm going to make this a reference angle. Okay, so now, and again, it was already positive, so you might be thinking, Mark, is that really necessary? I'm going to say yes, because the one solution that you are going to find by taking arc, because see, that's the thing. When you take an inverse function, because that's how we're going to solve this thing. We're going to take the arc tangent of both sides here. That is always going to give you just one solution. So I don't like to say, oh, theta's this. That's the one solution that you get, because it's not, right? You're getting a reference point for something that's hopefully going to generate all the other solutions for this trig function. So I typically like to make it so that we're solving for a reference angle here. So taking the tangent inverse of both sides, if you literally plug tangent inverse or arc tangent of 1 into your calculator, you're going to get pi over 4. Actually, you're probably going to get some decimal, whatever pi over 4 is, so long as your calculator is in radians. But again, that's a reference angle. Now, luckily, pi over 4 is going to be one of the things that we use to generate our solution set, to generate at least one of them. Because that was part of the equation anyway. It was already positive, right? This wasn't there originally. Pi over 4 is one of the things that when you plug it in, you do get positive 1. So, but if we were looking for negative 1 and then we solved for a reference angle, so I put the reference angle back in, this became positive, then this is purely a reference angle and actually won't generate one of our solutions. Anyway, pi over 4 is here. And the reason we get 1 for tangent is because both sine and cosine are the same at pi over 4. However, there's another quadrant that also gives you positive stuff for tangent, and that's at 5 pi over 4. Right? They're both, sine and cosine are both negative, so when you divide them, you're still going to get a positive. So then, okay, anything that's coterminal with these things as well is also going to be a solution. So we could say this, right? We could say pi over 4 plus 2 pi n is one set that generates solutions, and then 5 pi over 4 plus 2 pi n is another set that generates a bunch of solutions for us. But the thing to notice here is that for the tangent function, the period is not 2 pi. The period is actually pi, which in fact is the angle distance between these two angle measurements. Right? Pi over 4 and 5 pi over 4 are a pi distance away, right? A pi angle measure away. So we can actually combine these two things into just being pi over 4 plus pi n, because if n is 1, then you have pi over 4 plus pi. Well, that's 5 pi over 4, right? That's here. Then you add pi, you get here again. Then you add pi, you get here. Then you add pi, you get here. And then here, and then here. So you can actually, for the tangent function, the period of the tangent function is a single pi instead of 2 pi. So typically it's kind of starting value plus period of trig function times n, and for tangent and cotangent, that's pi instead of 2 pi. There are some things that can alter the period, as you know from, hopefully you guys watched the video on transforming trig functions. You can alter the period, certainly, and that's going to change how this thing plays out. But for tangent, just know that you're using pi instead of 2 pi. Okay, example 3. Let's say that we want to solve 5 tangent squared x is equal to 3. And this time I'm giving us an interval, right? It's on the interval 0 to 2 pi here. Okay, well that's nice. So first I'm going to divide by 5, and then we'll take the square root of both sides, so we get tangent of x is equal to plus or minus the square root of 3 over 5. So I'm going to break it up into both plus and minus pieces, just to really separate that there are actually two equations here. But then I'm going to talk about the reference angle, which kind of combines them into one case again. We just have to cognize that tangent is allowed to be both positive and negative, which actually means that our answer is going to be, we should have 4 answers when we're done. And I know that because we're doing we're talking about one full period for sine and cosine. So we've got quadrant 1, 2, 3, and 4 all contained within this interval. And tangent is either positive or negative in all of them. So we were going to end up with 4 solutions here. Okay, so we're going to take the arctangent of both sides of this thing, and we get that x sub r, right? The reference angle for x is the tangent inverse of square root 3 over 5, which is 0.659. It's not a nice, happy radian measurement on the unit circle that we know, so I rounded it to the 3rd decimal point, right? 0.659. And that is certainly a solution. That is the quadrant 1 solution. In fact, 0.659, that is less than pi over 2. I believe it's less than pi over 3. It might even be less than pi over 4, but I don't know that for sure, so don't quote me on that. So it's like around here. This is one of our solutions. That's the quadrant 1 solution for this thing. But then there's also going to be that same thing in quadrant 2, in quadrant 3, and in quadrant 4. We just need to figure out what those are. So here's how we would do it. To find the second one, you have to cognize that the reference angle is this, right? The first solution kind of coincides with what the reference angle is, which means that this angle right here is 0.659. So if I want to figure out what that angle is, let's do pi minus 0.659, and we get 2.483. Okay, so that's the quadrant 2 solution for this equation. The next one, right, has also a reference angle of 0.659. In fact, all of the quadrants have the same reference angle. So to figure this one out, we would have to do pi plus 0.659, right, because we're at pi here, and we're going an additional 0.659. Well, that's 3.800. And then I think the digit after that is a 5, but I decided not to round it. The quadrant 4 angle has a reference angle of 0.659, as they all do. So to find this one, we can do 2 pi minus 0.659, and that's going to give us a solution of 5.624. And those are finally all of our solutions for this thing. So this time we were given an interval, but we had to use the reference angle to find all the possible solutions for this because tangent is plus or minus in all of the quadrants. So that's why we have 4 solutions here. Last one. Let's say we want to solve the square root of 3 times the cosecant of 4t is equal to negative 2. Okay. Now we were just talking about how you can alter the period, right? This is a case where we're altering the period. The period for this thing is 1/2 pi. Remember, period's equal to 2 pi divided by the b, which is the thing inside of the parentheses, inside of the function that's being multiplied by your independent variable. So 2 pi over 4 is pi over 2. So 1/2 pi is the period for this thing. So anyway, first thing we're going to do, nothing really changes at the start. In fact, what might help, in hindsight, I should have done this. I should have said something like, let's let 4t be equal to theta, because then we could just write theta here, and we could treat it exactly the same up until we get to the end. I did not do that, but that is something that if I were to redo this entire slideshow, I would put that in. But I'm not going to do that. At this point, though, I want you to notice that we're looking at the cosecant function, and I don't like to look at the cosecant or the secant or the cotangent. I typically like to just look at sine, cosine, or tangent. So I'm going to go ahead and flip this thing by a reciprocal identity. So the cosecant of 4t is equal to negative 2 over square root 3 means the sine of 4t, which is the reciprocal of cosecant, that's negative square root 3 over 2. I'm going to take the arc cosine of both sides. I'm going to make it positive. This is actually the first situation where we're making this positive because I want to just look at a reference angle here, which is good because I know where the sine of something is equal to positive. This is positive now because we're looking at a reference angle of square root 3 over 2, and that's at pi over 3. So 4 times the reference angle is pi over 3. Right? Which means that 4t could be, and so by the way, this is the reference angle, but in my head, I'm like, okay, well, wait a minute. We're solving for when sine is negative. Sine is negative in quadrants 3 and 4. And so the pi over 3 angle right, the thing that creates the pi over 3 reference angle in quadrant 3, that's 4 pi over 3. The thing that creates the pi over 3 reference angle in quadrant 4 is 2 pi minus pi over 3, and that gives you 5 pi over 3. And then I'm just adding 2 pi n, right? Because that is anything that's coterminal, right, with these things is also going to be a solution to 4t, right? But we don't want to solve for 4t, we want to solve for t. So at this point, I would divide everything by 4, including the thing that we're adding, right? Including the 2 pi n part. So if I divide the entire top equation by 4, I get t is equal to 4 pi over 12, which reduces, and I'll do that here in a second. But then now the period isn't 2 pi anymore, it's pi over 2. So it's plus period n. It's plus pi over 2n, or 1/2 pi over 2n is how I wrote it here, where n's an integer. Okay, but 4 over 12 does reduce to 1/3. So pi over 3 plus 1/2 pi n is our first generating set. Our second one, dividing by 4, is 5 pi over 12 plus pi over 2n, where n's an integer. Okay, so the thing I wanted to point out here is when you alter the period, you're altering your what you're adding. You're altering the coterminalness of it, because they're coterminal in their own function, right? We're not working on a normal 2 pi period anymore. Now we're working on a period of pi over 2. So that's where things start to repeat themselves. Okay, so not only does the value, the angle itself, get divided by 4, but the period also gets altered when you're changing it like this. And if you look at the graph, right, I graphed this thing in Desmos, right? Here's all the values before 2 pi. So if I put on like here, like this would be like maybe the interval from 0 to 2 pi or something, then you'd have 2, 4, 6, you'd have 8 solutions for this. It's basically anything that's still below 2 pi. So I would honestly, I would start here and just start adding pi over 2 to it until I exceed 2 pi, and then I would not include that one in the solution set. Then I would start here and just start adding pi over 2 until it's past 2 pi, and then not include that one as well. But you'll get 8 solutions if we were going to use an interval like this. So hopefully you guys learned something. Hopefully that made sense. This one was a little hard to write, but yeah, you guys can be the judge of how things went. If you have any questions, leave a comment below. Thanks a ton for watching, and I'll see you in the next one.